Hello, I am Nahid Hasan from Daffodil International University from Department of Electrical and Electronics Engineering. Here, I am presenting our research paper. The title of our research was Design of High Gain and Wideband Circular Patch Antenna based on defected ground structure for 28 GHz 5G applications. Here, we have designed a single band 28 GHz antenna with defected ground structure that could enhance or achieve a wideband operation through a systematic design and optimization. Our approach achieves remarkable bandwidth enhancement from 0.75 GHz to 5.78 GHz, covering frequencies from 26.43 GHz to 32.21 GHz. Resulting in an impressive impedance bandwidth of 20.5%. So here we have also achieved a remarkable return loss improvement on return loss from minus 16 dB to minus 57 dB. Here we have also maintained a very good compact size which size was very compact, and we have used a substrate of epsilon value of 2. And now we discuss about the introduction part. Here we have discussed about various research papers which are published previously with similar topics. Here in some references they proposed a dual band antenna with a modified ground plan exhibits operational bandwidth of approximately 1.23 GHz at 28 GHz and 1.06 GHz at 38 GHz, here we can see these bandwidth are very narrow at both operational frequencies. After even they have used some defective ground structure, but they didn't quite get any improvement on bandwidth. And we can see another work where their bandwidth was 21.5 GHz to 24.3 GHz, and another was 33.9 GHz to 36 GHz. The antenna offers wideband operation, bandwidth, high gain, and compact size advantage. Yet their complex structures pose a hindrance. So that is a problem. In another reference, we can see the antenna setup features a defected circular shape radiator with a modified ground plane operating from 23 to 28 GHz with a maximum gain of 5.85 GHz. However, despite this performance, the antenna is relatively large. Its size is not compact. So, in contrast, an arc-shaped millimeter wave antenna offers a bandwidth of 4.41 GHz and a gain of 4.49 dBi. And here we can see the bandwidth and the gain is quite low. So we are aiming on achieving a higher bandwidth from this and a higher gain from this using defected ground structure. So in our work we are aiming for those parameters improvement. In addressing the contours observed with prior designs, our paper introduces a compact antenna designed for operation within the millimeter wave 5G frequency spectrum. Our proposed DGS techniques boosts antenna bandwidth while maintaining a decent gain without adding extra complexity or without increasing its size. So first of all, we have designed a conventional antenna without any complexity or without any defected ground structure. Just we are using this formula to calculate the radius of our conventional antenna, which we can see in this picture. This radius r was calculated from this formula. Here we can also see other dimensions of our antenna, which is radius, substrate height, ground height, substrate length, etc., inset length, inset height, inset width. Those are mentioned in this table, and we can also see the conventional antenna on figure 1, A, B and C. Here we can see in this three picture A, B, C, we can see nothing of defected ground structure, a conventional antenna which was resonating nearly at 27 gigahertz, and with a very narrow bandwidth, which is approximately 0.75 gigahertz, and a very poor reflection coefficient, which was minus 16 dB. We are trying to improve these both sides, that we want to improve our return loss and also as well as bandwidth using defected ground structure. So we also have to mention the gain of our antenna, which was at first the conventional antenna gain was 6.71 dBi. We want to maintain a decent gain, even if we increase the bandwidth. So this is our main target of this research. So we can see our conventional antenna in this picture, and after some modifications, we are using defected ground structure. We have two different defected ground structures. At first, we can see on figure 1D, here we can see we have decreased the length and width from both sides of our ground. So here we can see AX decrease from length and width. Here we can see in this picture, we can see that different value of AX, for different value of AX, as well as our first step of defective ground structure. We can see that a larger bandwidth was achieved. This is our first step of achieving a good bandwidth. So this step also proposed a various value of AX, that if we use different dimensions of AX, the ground plane achieves different bandwidth in different frequencies. So here we are taking a value of AX 0.175 was proposed, because we can see this black curve was achieving more efficient and good resolution on near 28 gigahertz with a very good bandwidth. At this stage, our proposed value of AX is 0.175 gigahertz. But we can observe, though here we have some also good improvement on return loss, which was minus 16 dB to minus 43 dB. So we have already gained a very good deflection coefficient from before, but we are aiming a better reflection coefficient than that. So after that we are experimenting with another structure within the same defected ground structure we proposed on figure 1d in this picture. Now we want to cut a very thin very thin circular path over here, circular ring over here, with a thickness of A. Here we can see that the value of before the circular ring, we have also we have the value of AX 0.25 0.17. There is also a table here that we can see the different value of AX, the different reflection coefficients and different bandwidth. So here we can see this is the best combination at this stage. So we are taking this as our proposed form of AX. So after that the value of A also has been also analyzed. Our thin circular ring here in this section, we can see while maintaining the main structure, main defected ground structure with AX. At this defected ground, we have added a very thin circular patch, circular ring, with a thickness of A. In this section, we can see we have maintained our previous defected ground structure AX 0.175, and we are experimenting with different values of thickness A, the ring thickness A, and we can see that if our bandwidth did not increased or decreased. So as well as there is no effect on our bandwidth, but there is a larger effect on our return loss, that we can observe. Our return loss was mainly minus 23, minus 43, minus 39 dB, minus 42. This was the range while we have working with AX. But now after cutting a very thin circular ring, we were achieving very good bandwidths, minus 54, and we have proposed minus 57 dB. So we can see after cutting a very thin circular ring, we can achieve a more better, we are achieving a better return loss. So after that we were experimenting with our value of A, which was 0.05 millimeter. With this we were experimenting with different value of AX, so that we can be sure that which combination is good for our antenna. So at both this picture, we can see the value of AX and A are same, with same combinations. So we are proposing this value of AX and A. So here we can see that the table, that with same value of AX and different value of A, and we are proposing this combination over here, which was achieving minus 57 dB. After that, this picture has shown the different value of AX and the same value of A we proposed here, and we can see the reflection coefficients and our reduced length. So both of this table confirms that the same combination. Also here we can see, although we have improved our bandwidth and return loss at the same time, we have also maintained a very good gain of our antenna, which was 5.78, which was mainly 5.123 dBi of peak gain. This is a very good combination of antenna, with a decent gain, a good bandwidth, and a very good return loss, and with even with a compact size. In this section we have discussed about the voltage standing wave ratio, which is mainly mainly related to our return loss, or our deflection coefficient graph. Here we have also marked the area of our bandwidth, and in this section we mainly discuss about what is a voltage standing wave ratio and its formula, and also discussed about the surface current. This surface current surface current with defected ground structure and without defected ground structures. And Here we have discussed about the antenna gain and efficiency. Here we can see our antenna gain is 5.123 dBi at 28 gigahertz, which is a very good improvement. And we can see the efficiency in this graph, and the radiation characteristics. Here we can see the radiation characteristics, our radiation without defected ground structure and with defected ground structure. We have also compared our both gain pattern, and which is a very similar pattern with some different structures. And the radiation characteristics illustrate here how an antenna emits energy in different directions. We can see that in figure 6AB, the radiation characteristics of the antenna with a defected ground structure are presented. The findings reveal that the antenna attains a maximum gain of 5.123 dBi observed in the direction of 12 degree. Likewise, the three-dimensional radiation pattern incorporating defected ground structure DGS is illustrated in the figure 6B. Figure 6C and D depicts the radiation characteristics in E plane and H plane of the conventional antenna without any defective ground structure, which was achieving a maximum gain of 6.71 dBi. There is a very good improvement in bandwidth. The gain was decreased at some scale, but although we have maintained a very good gain through time. In this section, our comparative analysis with different works was shown here, that our which is proving that our antenna size was very compact, and we have gained overall a very good bandwidth from more research papers, and we have also achieved a very good peak gain, and a remarkable reflection coefficient with a good efficiency. And here is our reference section. We have referred various paper from various journals, and the research paper was funded from the Division of Research of Daffodil International University. And here is the author section. We were working with we were a team of 4 authors, and overall here is our presentation, and thank you very much for hearing.